Good afternoon, everyone, and thank you for taking the time out of your busy schedule to join us for today's webinar, The Importance of Calibration and Maintenance of Gas Detection Systems. My name is Oksana Broda, and I'm a webinar facilitator here at Lesman. I'd like to introduce John Greivell, who's our speaker today. He's the Vice President of Lesman Instrument Company, and he heads up the gas detection, analysis, and industrial hygiene segment of our business. John has been involved in the environmental health and safety field since 1990, working in the areas of RCRA remediation, emergency response, confined safety entry, site-specific safety plan development, and the development of monitoring strategies for these types of projects. He's been a guest lecturer at the UW system and has given technical presentations for the local and state safety and industrial hygiene groups on a variety of monitoring technologies, applications, and best practices. I'm going to hand it off to John so he can start the presentation, or we can maybe wait a little bit and let the people join us. John, are you here?
I am.
All right. Do we want to?
Yeah. Thanks, Oksana.
All right. All right. I'm going to mute myself, and I'm going to monitor the questions in the chat box here for the remainder of the presentation.
Perfect. Appreciate it. So thank you, everybody, for joining us for a very quick discussion about maintenance and calibration of fixed systems. To start, I'm not a fan of talking at people, but unfortunately, that's what we have with this GoToWebinar format. Your microphones are muted, but there's a chat function that Oksana mentioned in the question box, and that she will be monitoring, and we'll pull those questions up at the end of the webinar. I want this to be useful for everyone, so I need your input to make sure we hit the mark. So please keep those questions and comments flowing. Also, a preemptive apology for my voice. I woke up this morning with a bit of a sore throat, so I think it's going to get a little scratchy towards the end. Please bear with me. So when I started in this business, fixed gas detection sensors were the size of a baseball. They're filled with liquid electrolyte, and your only option to detect combustible gas was to use a catalytic bead. We used potentiometers to adjust the zero and span. You usually had to go back and re-zero the sensor after spanning it, and then go back and recheck the span to make sure it hadn't shifted. You had to call the control room to let them know you'd be setting off alarms during calibration. If you forgot to advise the control room to inhibit the alarm inputs, you were likely to be hit with a deluge of the water system, or you'd be jumping out of your skin because a banshee horn fired off unexpectedly. Looking back, it seems archaic now, but back then those systems were state of the art. Since those days, all sorts of remarkable technology has been developed. Today we've got virtual reality goggles, we've got watches that can tell you that you're about to have a coronary event. So the question is, why can't we use all this technology to figure out how to minimize the amount of time spent on maintaining permanently installed gas detection systems? The reality is, manufacturers have been developing and marketing reduced maintenance technologies for decades. We've got fail-safe optical detectors, improved sensor performance with embedded predictive technologies. Not to mention the procedure for executing calibrations and maintenance has gotten substantially simpler. Even so, you still get monthly, quarterly, or semi-annual work orders for calibration and maintenance. Why? Why isn't there a simple answer on how frequently I should calibrate my sensor? It is the #1 question I get from people who are responsible for gas systems. With all the technology out there, can't they figure out a way to minimize or eliminate the need for calibrating and maintaining my system? Or my favorite question, how often do I need to calibrate these things? My quality program says I have to follow manufacturer recommendations. What are they? The quick answer is that no manufacturer is going to answer that question directly or concisely, and there's a good reason they can't. The salesperson may have implied that calibration is minimized or eliminated because of some inherent stability of the design, or that the system prompts you to calibrate it, but nothing gets you off the hook. Manufacturers will always state that it is up to you, the end user, to confirm performance of the system, regardless of the technology used. Even if the engineering team is fully confident of the technology and design, the lawyers will always weave in a hedge to cover something the engineers may have not anticipated. So ultimately, you own the system. You are responsible for its performance, regardless of the technology used to detect the gas, or whatever the salesperson implied. I am not a lawyer, obviously, but I think the Latin itsum iure faultus sums it up pretty well. The starting point is that drift and aging impacts everything, no matter what. It's not just potential variability between any two sensor elements or people. There can be various influences that impact the rate of the drift, faster or slower. Things like temperature swings, humidity swings, cross-interfering gases, gas exposure itself, contaminants, or even physical interference of the gas reaching the detector. You can design in things to measure the impact of most of these influences, but there will always be some confounding thing that no one anticipated or that you can't automatically detect or measure. And as long as that potential gap exists, nobody's going to sign up for your risk. As good as sensors have gotten regarding performance, stability, and self-check, and there's no question that they are far better than when I first started, I'd argue that you'd still want to perform routine maintenance check on your system. No technology can replace the value of putting eyes on a detector. At some level, you need eyes on the device to confirm that nobody put a baggie over it when they're painting the area. But it's not enough to just put eyes on the detector and confirm that it's not in fault. There are things you can learn to further build your confidence in the entire system performance. Let's look at some common maintenance activities used on these gas detection systems. First is a bump check, a confirmation that the sensor response to the target gas is exposed as expected. I put 20 ppm on the detector and confirm that it reads 20 ppm plus some tolerance. Next is an actual calibration, an adjustment of the output to match your calibration standard. Most of us are familiar with these activities from experience with portable gas systems. You bump before use, you calibrate at some interval or as needed. But if we applied the same logic to permanently installed systems, we'd be bumping them every day. Not at all reasonable. This is the spot where the new sensor technologies fill the gap. The other type of test is a system check, performance check. But this gets very tricky unless you have a clearly defined scope of work. We're going to dig into this a little bit later on. So what can and can't you learn from each of these maintenance activities? A bump check confirms that the sensor still responds to gas within performance expectations, within limits. When you put gas on the detector, do you measure the time it takes to reach your target concentration? Is that part of your performance expectation? Most newer design transmitters allow you to bump test a sensor without setting off alarms by going into some sort of maintenance mode, holding the outputs to the control system. But I'm not aware of any that have a timer function to reach the target level during a bump check. And of course, unless you force the output, you also don't know if the alarm functions are still operational. You can say that the sensor responds to the target gas within your acceptable tolerance, but you can't say anything about the rest of your system. Calibration puts eyes on the detector and adjusts the output to match your target. It adjusts for the aging and drift that we all experience. As with a bump check, though, most newer sensors isolate the output during calibration. If you've ever set off a deluge system by mistake, you appreciate this feature. The potential consequence, though, is that you don't know if the rest of your system is functioning as expected without further testing. So with calibration, you can say the sensor responds to the target gas within a smaller tolerance, which is typically the gas calibration error range, gas cylinder calibration range, but you can not really know anything about the rest of your system without further testing. This brings us to the crux of today's conversation, the performance check. As mentioned before, there's no specific definition on what this means. So clearly identifying the scope and the steps required is critical, but I look at it as a check from tip to tail. You check everything from detector performance to the alarm outputs and their functions, right down to the employee behaviors that you want and expect. It is the hardest part to plan and organize, but it's the only way I know of to confirm the system and the people are functioning as originally designed. I have some examples of where these maintenance activities can teach you things you might not expect. First is a pretty rare situation because usually I'm getting yelled at. So I was taken back when a process engineer complimented me on the performance of an LEL sensor, catalytic bead. He showed me the data going back for weeks on his data historian. Sensor was showing a rock steady 0% LEL output. Instead of taking the compliment, I asked him, "Do you believe it?" His answer to me back was, "What do you mean?" And my question to him was, from what you know about the performance of your process, do you think that steady zero output makes sense? The background is the sensor location is near a vent that historically released small amounts of solvent vapor, not alarm concentrations, but not zero either. So we ended up walking out to the site and we found that the sensing point that was solid zero on the data historian had a waxy buildup all around it. There's absolutely no way for the gas to get to the sensing element. The history here is that this company did have a very sophisticated calibration and maintenance program, but as we dug in a little deeper, the function had been transferred to a new technician. When the technician was out doing his rounds, he did not see the sensor because it was completely plugged up with wax, didn't look like a transmitter, assumed it was a missing tag. So only putting eyes on the sensor could correct this or catch this. Example 2 is a little bit scary because it hits close to home. We measure LEL levels inside drying ovens. This is a relatively new system. When we put it in, as we do with all startups, we checked everything right down to the interlocks. About a year after we installed the system and commissioned it, I got a frantic call from a customer that they had an event and that my gas detector didn't work. I dropped everything, grabbed my calibration equipment, rushed over to the site. When I got there, everybody was on pins and needles, and I got the distinct impression that the assumption was my system had failed. For reference, the event had resulted in a blowout panel on the ductwork leaving its location. So I went to the detector and did a bump check. Everything looked great, still right on the button. Continuing to dig, I did a system check where I put gas on the sensor to check the outputs. Again, everything looked great from the sensor side. Eventually, after more digging, we discovered that the sensor input to the oven controller had been defeated. My sensor had been screaming high gas, but the receiving system was not listening. Somebody had decided that the alarm was annoying and was impacting production rates. The good news was that nobody was physically injured, although a couple people ended up losing their jobs. A standard bump check or calibration, since the outputs get isolated in these new technology transmitters, would never have uncovered the situation. Only a performance check would have been able to test and expose that. Next example is more common than I like to admit. I was walking a site during a project review and I saw a red beacon going off. My nature is to be a little bit curious and nervous, so I asked what the red light meant. As a general rule, red lights in my world don't mean good things. Almost on cue, I got 3 different answers from the 3 people I was with. None of the answers were good things to have happened. One said there was a tank overflow indication, one was a high temperature alarm, and the other was a gas alarm. Regardless of who had the correct answer, the issue was that none of the operators in the area were paying any attention to the light. So in this situation, the most technologically advanced sensor with internal self-checks and super duper automatic self-calibration capability, and if something like that existed, would not have helped this situation. Only a performance check and employee training could have fixed it. In the last example I'm going to share, I had been invited to a customer site to scope a system calibration project. Part of my process is to learn about the history and experience with the existing systems. So I asked the customer who had been doing the calibrations to this point. I was originally told the safety team. So I checked with the safety team. They let me know that it had been handed off to the maintenance group. Checked with the maintenance group, who responded, we used to do this until Fred retired. That's when we handed it back to safety. Once we had the maintenance history figured out, we went up to the detector and discovered that the operator who worked closest to the system had developed a complete lack of trust in the system. Didn't believe any of the results and likely would not have responded to any alarm event. Again, the ultimate end product of any detection system is safe employee behavior. In this case, calibration, a clear explanation of technology, a system and employee training were needed to get the system and the correct employee behaviors back on track. So we've discussed terms and shared examples of what to avoid, but the open question is still, what should my maintenance interval be on my gas detection system? I'd suggest a real question to ask is, does your team and do you trust the information your gas detection is providing? Most importantly, will the employee behaviors during an alarm condition meet your expectation? Do they move and react in the way they're supposed to, or do they look around confused about what the horn means? This has to be the starting point. If the answer is yes, it sounds like you are all set with your maintenance interval. Congratulations, keep it up. Don't forget that people forget. So weave the system reminders into your training plan and keep everybody up to speed, and keep asking yourself, do we still trust the system? If your answer is no, employees aren't trusting the system or responding appropriately, then you need to dig in a little bit deeper. Find out what the issue is, what's driving this lack of trust. Is the remedy bump checking, calibrating, training, some kind of combination? Once you figure that out, decide on the best resources to support you in the corrective action steps needed, whether those are internal or external resources. Invest in the system until you can answer yes to the trust and behavior question. Then you can start looking at backing down the intervals. Gas detection systems get installed for any number of reasons: a near miss event, an employee request, insurance or corporate requirements. Whatever the reason, they're designed for a purpose. A light and a horn or an interlock or whatever was set up to happen under certain conditions. And with those functions, there were certain employee behaviors that were expected as well. Thankfully, years tend to go by before gas alarm trips happen. The struggle is that during those years, stuff happens. Sensors drift, lights burn out, people get reassigned, and all of a sudden, nobody responds to the alarm the way you wanted them to. So the right frequency and maintenance tasks can help you keep your gas detection system that includes the employee behaviors working the way you want to and need it to. So the takeaways: set a reasonable frequency for sensor calibration. To define reasonable, factor in the risk. If your team, for whatever reason, didn't respond to the gas alarm the way you wanted them to, how big of a deal would it be? What would the consequences be? Let that inform your frequency of self-check. Keep in mind that older sensors tend to drift more than younger ones, just like us. It takes me a heck of a lot longer to recover from a run than it did a few years ago. And by sensors, I'm not talking about the transmitter or the electronics. I'm talking about the sensing elements themselves. Typically, they drift more the older they get, the closer to end of life they get. The other habit to consider is to check your sensor and system after any high gas event. Make sure nothing got damaged or exceedingly aged from the exposure to the gas. Confirm the system still works as expected. And if the employees respond as expected, make sure to encourage and applaud that behavior. Finally, I'd suggest that separate from the sensor calibration and maintenance work, that you set some interval to do full system testing, right down to the employee level, right down to the behaviors. This is the biggest area for potential improvement in most industrial gas systems that I see. Thank you for listening. I'm hoping I triggered some questions. Oksana, what do you have?
So I have a few questions here. So a customer's asking, a vendor told us IR sensors don't need to be calibrated.
That's a technology question. So there are ways that you can make sensors self-report, right? So technically the answer is you don't need to calibrate them. The point I make is that still doesn't confirm performance of your system. So even if you don't have to adjust the output on the sensing element, that doesn't mean that your sensor functions or your system functions the way you intended to. And again, the endpoint is that the employees are behaving correctly. It's one of the potential pitfalls of having sensors that people don't have to touch or maintain. People start to forget they don't have to worry about them. And again, because these gas alarms don't typically happen every week, they get further and further back in people's memory. And without training and retraining, it's such a circumstance that people start to lose, they lose their behaviors.
All right, I have another question here, John. The question is, we've always calibrated our system quarterly. Can I go to 6 months?
So the same question. I clearly understand that question. The need to try and do that. We all wear multiple hats. Everybody's working their tails off these days. I go back to the answer, and I apologize for being a little bit squirrely on trying to not give a direct answer. I go back to the question, and the question is, does your team respond appropriately? I would suggest that if you have 100% confidence in the behaviors in the alarm system, that you can try backing it off to every 6 months. Again, if your safety team, if your risk evaluation folks agree, you can certainly try backing it off. But if there's any gap, if there's any potential failure mode of employee behavior or alarm system, I'd step it back up. It's a circumstance where these are systems that you don't need until you need them, and then you really need them, right? That's the typical gas release scenario. So my nature is to say I'd rather have you do it more than less, but you've got to answer that question: is do you feel confident in the system?
And it looks like a final question here. Well, calibration is easy and our people know how to do it. Why should we pay someone else to do calibration for us?
You shouldn't. If you've got control of your system, there's no reason. As I said, in the early days, they were a pain in the tail. There's interplay between the zero and the span pots, and it was almost an art form to get a calibration to hold and be right. Nowadays, it's been automated and simplified with the electronics and the interface on the transmitters. I go back to that same question. If your team is confident in the results, then your system is working fine. Whatever your program is working well, keep it up. If you run into a situation where, for whatever reason, employees don't have faith, it might make sense at those times to bring in a third party to support your efforts, to support your strategy, just to be a sounding board. That's where those things have some incremental value. But absolutely, if you have the time and you've got the program in place, there's no reason to pull in a third party.
Thanks, John. How does a catalytic bead sensor function versus chemical sensors?
Simple terms, catalytic bead is a Wheatstone bridge. So you've got a measurement bead and a reference bead that doesn't get exposed to the gas. If you think about it, it's a temperature change. So the leg that's exposed to the potential combustible gas heats up that leg of the Wheatstone bridge, and the resistance change that you got from a heated wire versus a temperature controlled wire to keep that circuit balanced is where you measure the energy flow, and that correlates back to the gas detection. The gas concentration, you calibrate it that way. In an electrochemical sensor, it's just a redox reaction. You've got an anode and a cathode, and you've got an electrolyte, and you're relying on some gas to diffuse into the sensor and create a reaction that generates that picoamp or tiny voltage output to generate the signal. Just touch on this again. The catalytic sensor, this Wheatstone bridge, is described as a dumb sensor. So we use the example of a baggie. So if you think about ways to defeat a transmitter, if you put a baggie over it, if you put a baggie over the sensor, no gas can get to the device, and then your system is not doing anything, right? So that's that core value of putting eyes on it. The reason these things tend to drift is if you look at a catalytic sensor, the catalyst material. Unknown caller. Oh, sorry. The catalyst material, it ages, it wears. There's poisons that can coat it. There are acids that can etch it. So it's constantly in the process of rebalancing that circuit. You have to zero it and put time and energy into it to keep it trued up. In the case of the electrochemical cell, in theory, these chemical reactions are bidirectional, but that never works out. These things always age. Unknown caller. Sorry. They age, and that's the chemistry just starts to change, and that's why you have to put in time and energy to keep truing it up.
I have a comment here that says catalytic bead is combustible and electrochemical is toxic.
Yeah.
And
correct.
A follow-up question, what is the normal life of a catalytic bead sensor?
I love this question. So how about from soup to nuts is the answer. So there are catalytic bead sensors that have been out and performing and calibration, holding calibration, that are 10 years old and longer. They're catalytic bead sensors that last a year or two. It's all based on the environmental situation. And it's all those influences that we talked about in the aging. Temperatures, contaminants. If you've got silicones as a classic example, if you're onto silicone material, you can coat a catalytic bead This is a circumstance where there's no way to detect the failure mode. You could spray, or the silicone could turn into a glass coating on that pellister, making it virtually useless. There's no way that the detector would understand that. There's no way to measure that. So you'd have a defeated system, not know it, and the only way to know it would be to put gas on it. So that's where you have to take a look at your technologies and balance that into your risk evaluation to determine frequency of calibration.
All right, I don't see any more questions. Does anyone else have any questions? Please type them into the question box before we wrap up the session. All right. Yes, there is another question. Is there a way to test the life of a catalytic bead sensor?
Yeah, so when you say the life, and this is hard in a one-way conversation, when you say test the life of the sensor, are you talking about the raw millivolt output? You can look at things like that and do some ballparking, but as a what we describe as a dumb sensor, it's pretty tough. If your question is, can you predict the next time you have to calibrate it? Experience would be more telling than.
John, there's sorry, John. There is a clarification. Is there a way to test the voltage of the catalytic bead sensor, not the life?
Sure. And on a lot of the transmitters, they will show you that. This gets back to something we didn't have time to touch on, but some of the calibration failure modes that these transmitters have nowadays, they put these measurements in place. So if this sensor doesn't have enough gain, doesn't have enough adjustment room to calibrate it to adjust to your calibration point, the transmitters nowadays come back and tell you that the sensor is failing. There is a lot of technology that gives you some predictive heads up warning about aging and near aging of these transmitters and sensors. The point that I was trying to make in the presentation is that technology is well established, it's out there, but the gap that I see more than anything is the example of nobody knows what to do when the light goes off. And that's the point I was trying to make with the presentation, is that regardless of the technology, if we don't exercise the process, if we don't exercise the alarm functions, and we don't exercise the expected behaviors, it continues to slip and slide. And unfortunately, with these kinds of systems, as I said before, when you need them, you need them. You don't want anybody to be scratching their head. You want them to be moving left and down to the rallying point, or you want the security to be coming in and checking on it, or you want the automatic valve to be shutting off flow. Those are the things that you need to have happen, because that's how you designed it originally. And that's beyond what the technology of the transmitter, the sensing elements can give you. I hope that answers.
I have a couple more questions, but this is a follow-up to that previous question. Can you test with a DVM?
That's what we used to do. So if you can get to the raw sensor output, that goes back to the old days when we used voltmeters and test points to look at the adjustment. In the old days, the transmitters didn't even have displays on them. You had test points and trim pots. So you look at the voltage and you adjust the voltage to read, whatever, depending on the sensor, 3.5 millivolts or whatever. That's how you make your trimming adjustments, not based on the concentration display, but based on the raw voltage. So if you can get access to that with a transmitter, the answer is yes. That's effectively what the transmitter is doing. It's looking at that data. Now that we've got all these sophisticated transmitters, it looks at that data and gives you all this predictive output.
All right. So here's another question. I tried doing a bump test on our Optima Plus unit using butane 49% LEL, and I could only get them to register up to 28% and doesn't seem to complete the bump test. Is it normal to be that far off?
This is a great question. So I think if I'm reading between the lines, this is a calibration curve. So when you give with combustible gas, whether it's catalytic bead or infrared, like an Optima, when you give it the gas, there's an absorbance, right? So there's an amount of signal at the core level, there's an amount of signal that gets absorbed. The amount of optical absorbance of methane, 50%, and butane, 50%, is different, as well as those absorbance lines. So if your Optima was calibrated to measure butane, then you want to use butane as your bump check gas, because otherwise there's a different value, different absorbance value, and the sensor doesn't know, right? So when you're designing your system, you want to make sure you're using the appropriate gas calibration curve, but then also you want to make sure you use the right span or bump check gas just to confirm performance. Hopefully, I hope that answered that question. That's a great question.
All right, and another one, John. Actually, sorry, I have a comment on that previous question. It was calibrated with butane at installation too.
So if it was calibrated with butane, if it's a butane calibration and the bump check only comes up, my gut reaction is make sure that there's not any that you got the right flow rate, that you're using the bump cap, so you're controlling the atmosphere inside of the optical chamber. I guess this is tough to do in this single direction conversation. If whoever is asking that question wants to shoot me an email or give me a call, I'd rather talk about it and figure out what the corrective action looks like. If it's a calibrated sensor for butane, and you gave it 50% LEL butane, it should come up to, darn near right on the button at 50% LEL. So if it's not getting there, there's something going on. So this gets back, well, I'd rather take this offline. So if
I'm gonna share your email address in the chat box so that anyone who wants to contact you directly can do so. Please check the chat box, everyone, if you have questions for John directly. I have another question here. Is it better to put a gas detector above the operator's head or near their feet?
This is another loaded question. So depends on the gas you're trying to measure, depends on the layout of the space and what you're trying to protect. So the thought process, it depends on, so think about where the source of the gas would come from. Think about the typical airflow of the space, the gas density. Is it a heavy gas, a light gas, or is it, more like carbon monoxide that goes where you put it? Those are the physical factors that are going to start painting the picture. Then you figure out what you want to protect. So typically what we try and do is you look at those factors and say, okay, what does failure look like? What are we trying to protect against? And then it's you kind of think through almost a gas dispersion model. So if it's a low gas and you're trying to protect an employee, when I say a low gas, a heavy gas, and you're trying to protect an employee in the breathing zone, then you'd put it lower than over their head, right? If that seems to make sense. If it's a light gas, you do just the opposite. Hopefully that addressed it clearly.
All right. Another question is, when calibrating LEL sensors, can you interchange testing gases, for example, hydrogen or methane?
Hydrogen and methane tend to be pretty close on a catalytic bead. Again, it depends on what you're trying to do. There's different sensitivities that you can select. So how do I answer this? There are adjustment factors, right? So just like we talked about with the Optima, with the infrared platform, if you put 50% methane on a sensor and it's calibrated to methane, it's going to read 50% LEL, 50% LEL methane. If you're trying to adjust that output to read for ethanol, you may want to give it 50% LEL methane, but make the readout 29% or something, right? And we've got tables that we use for establishing that ratio. So if you're talking about calibrating, my feeling is when you set the system up, you have the detail of you use this check gas to get this result. And if you vary that, I'd go back to the manufacturer and triple check and confirm that the switch from methane to hydrogen doesn't have any sort of correlation offset difference. It shouldn't. It should be relatively close, but it's still worth a check.
All right, another one, John. Sometimes the sensors are at the end of their life cycle and the alarm goes off, even if there is no hazardous condition. Is there a pattern you see in faulty sensors? I have this experience with oxygen sensors.
Yeah, so as I said, as sensors get older, they get, I'm going to use the word finicky, a very technical term. They get a little bit more jumpy, a little bit more finicky. As a general rule, if it's oxygen, the default is to go downscale, right? So as they age, the output with ambient air starts to decrease, so that your reading starts to drop down. And in most of those situations, the alarm set points are down. So you can have a sensor that drifts, and it drifts faster the older it gets, but you can have it drifting into alarm situations or being more sensitive to slight changes because the signal is amplified so much because there's not a lot of raw signal left. But it holds true for any sensor, right? That's the whole purpose of the bump check or the calibration interval, is to make sure you capture it and you make sure that you get an opportunity to replace it before that happens. The thing that I see, I keep going back to it, it's employee behaviors. If the employee is conditioned that the alarm doesn't mean anything, it just means the sensor's old again, that's not the behavior we're trying to train into them. If the light's supposed to mean I go to the rally point or I go to my supervisor's office or whatever I'm supposed to do, I want that to happen automatically. And if I have a bad system or I've got an old sensor that drifts into alarm, the risk is that you start conditioning people to ignore. And that's a risk exposure that is, I think, not necessary.
All right, it looks like that's a wrap
Anything else?
on the question. No, looks like it on the question so far. Like I said, your email address in the chat box if anyone has any specific direct questions for you.
Great. And I really do appreciate the questions very much. This is, I think, more helpful than me droning on with my slides. It's again, the summary takeaway, it's, in my mind, it's always about the employee behaviors. Even if a system, and it's a gap that gets missed, I think more often than not, even if we test a system and the light works, the relay fires and the light lights, I keep coming back to this. You can test the mechanical pieces to it, the electronics of it, and say, yep, it's all working. But at the end of the day, there was an activity, there's a behavior that you expected. And there's nothing that drives me crazier than when you've got a red light flashing and everybody ignores it because nobody knows what the heck it means. That's just not the way we want these systems to be applied.
All right,
So,
John. Thank you for the presentation. I don't see anything else coming in here as far as questions go.
All right. Thank you, everybody. Really do appreciate it. If you've got suggestions for other content or other topics, please send either me or Oksana an email or send it to the Lesman email because we're always looking for ways to help. So let us know what we can do for you. Have a great day. Appreciate it, everybody.
This session has been recorded. We'll send out an email recording tomorrow, and you can also check our YouTube channel and our website for other recorded sessions. Thanks, everyone, for joining us today.
Thanks, Oksana. Appreciate it.
Bye, everyone.